You know, you do something about 20,000 times a day without even thinking about it. Breathing. But what if I told you that simple act could take us on a journey to the absolute coldest temperature possible in the universe? Well, today we're diving into the hidden and seriously powerful laws that govern gases. Let's get into it.
I mean, it seems so simple, right? So automatic. But have you ever really stopped to think about what's physically happening every single time you inhale and exhale? What are the invisible forces at play?
Turns out, the secret is this amazing interplay between three pretty simple things: the pressure of the air around you, the volume inside your chest, and a scientific rule that someone figured out hundreds of years ago.
Okay, so to really get this, we have to start right here with our own bodies. Let's actually break down the mechanics of taking one single breath.
It's really this elegant four-step dance. First, your diaphragm tightens up and flattens out. That simple move actually makes the space inside your chest bigger. It increases the volume. And with more room, the pressure inside your lungs suddenly drops. It's now lower than the air pressure outside. And that's when physics just takes over. Air rushes in to even things out.
And get this isn't just some neat comparison. The U.S. National Library of Medicine says it flat out. This entire process is a living, breathing demonstration of a fundamental law of gas physics. It's called Boyle's law.
All right, so let's put this law under the microscope. What in the world did Robert Boyle figure out way back in the 1600s that explains how we're breathing right now?
The key thing to grab onto here is that word inverse. Think of it like a seesaw. If you have a container of gas and you squeeze it, making the volume smaller, the pressure inside goes way up. If you let it expand, giving it more volume, the pressure drops. One goes up, the other goes down. It's that simple, as long as the temperature stays the same. And this picture, it shows you exactly what we're talking about. This is a lab setup designed to prove Boyle's law. See the syringe? As you push that plunger in, the amount of space, the volume, for that trapped air gets smaller. That forces the pressure up, which you can see because it's pushing the water up that little glass tube. Less volume, more pressure. That's Boyle's law right there on the lab bench.
Okay, but what happens if you start messing with the one thing Boyle's law told us to keep the same? Temperature. Well, for that we have to turn to a whole different principle, Charles's law.
Now, this law, which Jacques Charles worked on back in the 1780s, brings heat into the equation. It says that if you keep the pressure steady, the volume of a gas is directly tied to its temperature. You heat a gas up, it expands. You cool it down, it shrinks. I mean, that's literally why a hot air balloon flies. Simple as that.
So let's just put them side by side for a second because it makes it super clear. For Boyle's law, you lock in the temperature, and you get that inverse seesaw, pressure up, volume down. For Charles's law, you lock in the pressure, and you get a direct lick, temperature up, volume up. They're really just two sides of the same coin, each telling us a piece of the story about how gases behave.
Now, I know what you might be thinking. This all sounds a little like high school chemistry class, right? But these laws have huge and sometimes life or death consequences out here in the real world.
Boyle's law is, and I'm not kidding, everywhere. A baby's very first breath, that's Boyle's law making it happen. A nurse drawing blood with a syringe, that works by increasing volume to drop the pressure. Even scary stuff, like a collapsed lung, happens when Boyle's law goes wrong inside the body. And if you're a scuba diver, well, understanding this law is everything. And this is where it gets really serious. Check out this quote from Stat Pearls. As a diver swims up to the surface, the crushing pressure of all that water around them gets less and less. So according to Boyle's law, what happens to the air in their lungs? It has to expand. If they hold their breath, that expanding air could cause a major injury. That steady exhale isn't just a tip, it's a life-saving move based on 17th century physics.
All right, now for the really fun part. Let's take one of these laws, Charles's law, and just push it to its most logical and kind of mind-bending conclusion.
So we know from Charles's law that when you cool a gas, it shrinks. Simple enough. But what if you just don't stop? What if you keep making it colder and colder and colder? Is there some point where the gas just has no volume left, where it kind of just winks out of existence? And believe it or not, that exact question drove scientists nuts for decades. First, you had Charles and Gay-Lussac figuring out the link between temperature and volume. But then this guy, William Thomson, who we now know as Lord Kelvin, he took the next giant leap. In 1848, he basically did the math backward and said, hey, there must be a temperature so cold that everything just stops. An absolute bottom.
And they actually came up with a number. This is it. Negative 273.15 degrees Celsius, or 0 on the Kelvin scale. They called it absolute zero. It's a theoretical temperature where all the little vibrating atoms would just freeze in place.
and the volume of a gas would, in theory, shrink down to nothing.
But even Lord Kelvin knew this was more of an idea, a fundamental limit of the universe. He wrote that it's a point we could never actually get to. It's like the horizon. You can walk towards it forever, but you can never quite touch it. It is the ultimate untouchable cold.
So there you have it. We started with the gentle pressure change that lets us breathe, and we ended up at the theoretical point where all motion in the universe stops. It's just two elegant, connected laws that describe the invisible world of gases all around us and inside of us.
It really makes you wonder, doesn't it? We went from the simple biology of a breath all the way to the very edge of theoretical physics. What other profound, invisible rules are hiding in plain sight, just running the whole show?